You realize that that's why I didn't want the 7 o'clock. Oh. Because in the evening you'll be tired. You'll be tired. And you went to campus. Hey. Hello, class. Are you with me? Okay. So what I'm saying is that if you want to infer causation or establish a causal relationship, then the statistical test or tools you need to use is the receiver operator characteristics curve, which is also called ROC curve. And out of the ROC curve, we have sensitivity, positivity, and area under the curve. Sensitivity means that if you have a rapid test kit, like the HIV test kit, and you realize that when you do the test, you check it on about 100 people, you realize that about 90 of them will be positive, then 10 of them will be negative. So the 90 that is positive gives you what? 90%. And the 90% is your sensitivity. So after sensitivity, we look at what? Specificity. So we can say that the test kit that you are using is highly sensitive. It's highly sensitive because it gave you about 90% sensitivity. And the specificity is so the sensitivity, so that means that 10% will be false negative. So 10% will be what? False negative. It's supposed to be positive, but it's negative. That means 10% is false negative, meaning that the 10% of the test kit is faulty. It is faulty, so it's not able to give you the positive results. Then we have specificity also, meaning that how specific is the test kit. Then we come to the area under the curve. They are all showing accuracy or precision of the test kits that you are using. Then we come to linear regression. We come to linear regression, then logistic regression. Please, are you with me? Are you with me? Okay. So let's go to the next. Let's go to you can't see the screen. Somebody, well, the first years called me right now. That's why I cut them. I've cut them. So let me share again. Are you seeing now? It's coming now. Okay, so I've explained the test that we use to establish causal relationship. So let's see. Can you see the slide now? Can you see cause and effect? Okay, so cigarette smoking will lead to what? An effect. And the effect can be what? Lung cancer. So this man sitting down here is sick of lung cancer. So we want to find out whether the lung cancer was caused by cigarettes or not. So cause and effect. The effect is the outcome. A positive association means that in the presence of the exposure or risk factor, we see a higher disease risk than we do in the absence of the exposure. This difference in disease risk is often measured by epidemiologists using measures of association called the relative risk and the odds ratio. Last time I explained to you what the relative risk is and what the odds ratio is. So if a positive association exists, the relative risk or the odds ratio will be greater than 1. Mr. Abdullahi, odds ratio is used in which study design? Mr. Abdullahi, I'm waiting. Mr. Agbeko. Agbeko. Hello. Oh, if I ask you a question, you have to answer fast because I'm recording. It will make the recording long. You have to answer fast so that the recording will not be too lengthy. I asked a question. I said odds ratio and relative risk. What study design do we use odds ratio for? Yes. Please answer fast then. Oh, please, who is answering the question? What about relative risk? Okay, so relative risk is used in longitudinal study. We use relative risk for longitudinal study design, and we use odds ratio for case control study design. But they mean the same thing. They mean the same thing. They are just going to show effect or how much of the risk factor causes the disease. So we say that when we get there, you understand. So in a positive association, if a positive association exists, then the relative risk or the odds ratio will be greater than 1. So 1 is always the reference or the standard. Above 1 means that the risk factor is able to cause the disease. And if it is less than 1, it means that the risk factor, the higher the risk factor, the lower the expression of the disease. If it's less than 1, it means it's a protective association. For instance, if you are looking at the odds of cigarettes causing lung cancer, and you get a negative association or odds ratio which is less than 1, then you can say that when you take in cigarette, it protects you from getting lung cancer, or it prevents you from getting lung cancer. Like some people are saying that, some men are saying that, especially the womanizers. They are saying that if you're able to empty your prostate gland, then it's going to make you not be able to get prostate cancer. How do you empty your prostate gland? If you are having sex with multiple partners, each and every day you are having sex, you are not going to get prostate cancer because you are emptying your prostate. You all know where the prostatic urethra is. So if you are having prostate, always having sex, it will open your prostate, the gland, everything will be fine, and you cannot have prostate cancer. That is somebody's hypothesis. So we can say that having sex will give you an odds ratio which is less than 1, meaning that having sex frequently protects you from getting prostate cancer. So a classic example of a positive association is smoking and lung cancer. Epidemiologic studies have shown that people who smoke are more likely to get lung cancer than people who do not smoke. So a negative association occurs when the presence of the exposure or the risk factor is seen with a lower disease risk. So this is it. So if you have an odds ratio, if the odds ratio is less than 1, the odds ratio is less than 1. For instance, example, if you have odds ratio of 0.6, then there is what? A protective association, protective effect or association. It means that the risk factor, you having too much sex, instead of you giving you HIV and other things, and instead of you having sex too much, giving you hypertension and prostate cancer and other things, it is rather protecting you from getting prostate cancer. And a second example is exercise. If you do a lot of exercise, your risk of getting hypertension will be equal to an odds ratio which is less than 0.8, less than 1 or equal to 0.8. We know 0.8 is less than 1, meaning that exercise protects you or prevents you from getting hypertension. So exercise has a protective effect from contracting or getting hypertension. But if you say odds ratio is greater than 1, it implies, especially if you have an odds ratio of 4 or 2.5 or 1.8, so we can say that 2.5 is almost like what? 3. So we say 3-fold. 1.8, when we approximate it, we get what? 2. So we say 2-fold. So we have what? You drinking alcohol has 2-fold or 3-fold or 2-fold increase risk of contracting or of developing or of having fatty liver or hepatitis. If you drink too much of alcohol, it will inflame your liver and give you hepatitis. So drinking alcohol has what? 3-fold or 2-fold or 1.8 odds ratio or 2.5 odds ratio of you being predisposed or getting hepatitis. So that's the meaning of odds ratio. And this same thing I've written, we can say is the same as what? The relative risk. And relative risk is for longitudinal study, whereas odds ratio is for, so we can change this one to relative risk. They are the same meaning and the same thing, but one is for longitudinal study, another one is for case control study. So I've explained this. So a negative association occurs when the presence of the exposure or risk factor is seen with a lower disease risk. For example, Exercise. If we define regular exercise as the exposure under study, then many studies have found that people who exercise regularly are less likely than sedentary people to develop heart disease. So we can see that in a negative association, the relative risk or odds ratio of people who exercise will be less than 1, meaning that exercise is a protective activity or has a protective effect from you getting heart diseases. So exercise has a protective effect from you developing heart diseases. We are still on causal association. Also in epidemiology, we say that a cause is a factor that plays a role in producing an occurrence of the disease, or a cause is what causes the disease. So it just plays a role. It's not a necessary part of the disease process. So we can also say that in epidemiology, the risk factor, it may not be only one risk factor causing the disease. It can be a whole lot of risk factors which come together to cause the disease, like you taking a lot of alcohol, you not exercising, you smoking. All these contribute together to give you metabolic syndrome or this heart attack, diabetes, hypertension. So for instance, we can talk about smoking being a cause of lung cancer, even though some people have never smoked also get lung cancer, meaning that smoking is not a necessary factor for all cases of lung cancer. So it means that some people do not smoke, but they also get lung cancer. So it's not only smoking that gives lung cancer, but there can be other risk factors that causes people to get lung cancer. So what are those risk factors that will cause a non-smoker to get lung cancer? I can say that people who don't smoke, for instance, your husband smoke, but you the woman, you don't smoke. But in literature, it has been found out that those passive smoking has passive effects, meaning that those who inhale the smoke, their condition is worse off than those who smoke itself. Because you are sitting there, you are with your husband, and your husband is smoking in the house, and you are just inhaling the smoke into your lungs. You would rather get the lung cancer, but not only the smoker will get it. Your case will be serious. So we are investigating that smoking is not only the smokers who get lung cancer, but the non-smokers, like the wives of smokers, the children of smokers, they also end up getting lung cancer. So causality. So we say that so if we have observed positive association, it leads to inference of causation. It leads to the causing of the disease. So smoking increases risk of lung cancer. So we say that smoking is a risk factor for lung cancer. Another observed negative association. The first one was a positive association. The negative association infers protection. We say that exercise decreases the risk of heart disease. Therefore, exercise protects you from getting heart disease. So for the first one, the odds ratio is going to be greater than 1. And the second one, the protective effect, the odds ratio is going to be less than 1. So an observed positive association such as between smoking and lung cancer could lead us to an inference of causation. We will then say that smoking increases risk of lung cancer. That is, smoking is a risk factor for lung cancer. An observed negative association such as that between exercise and heart disease could lead us to inference of protection. We will then say that exercise decreases risk of heart disease and protects against heart disease. Therefore, the use of risk factors and protective factor implies that you have made a decision about the causal nature of the relationship between the exposures and the outcomes under consideration. Okay, so I've already explained these ones. So how do we determine if an exposure causes a disease? This is an important decision for public health practitioners to be able to make, as it may be the basis for determining whether to mount a campaign to decrease this exposure in the community. So we are going to look at 7 steps or guidelines which will help us to be able to make meaningful associations and to decide the cause of diseases, employing various risk factors. So the first one is, so these are the steps. We have randomized trial evidence. No alternative explanation exists. Timing of the relationship is correct. Association is strong. Association is biologically plausible. Higher exposures lead to higher risk. Observed evidence is consistent. So let's see, does the exposure lead to the disease causation? We are going to see it. So for randomized control trial, this is what happens. The findings of randomized studies provide the strongest evidence pointing toward causality. So last time I explained to you that the highest level of study is the randomized control trial, because in these studies, chance alone dictates which participants are exposed and which are unexposed. So we see that in a randomized trial, a group of people are assigned to receive an exposure or a risk factor or an intervention, and these people are then followed over time to determine what proportion of them develop the target disease under study, which could be an illness but could also be a beneficial outcome, such as a decrease in blood pressure. So we can take about 100 workers or people staying in Boga. So out of the 100 people staying in Boga, we want to look at these 100 people, which of them will develop diabetes. So we follow them up and we realize that 70 of these 100 people develop diabetes. Then we find out what work do they do. Then we see that, oh, out of these 100 people, out of these 70 people who develop diabetes, about 80% of them are bankers. They go to work early in the morning, sit down till evening. They don't even exercise. So that is what led them to develop the diabetes. And you realize that those who did not, the 30% who did not develop the diabetes, what work do they do? They are Volta River Authority or VRA, the field workers. They just go, they'll be mounting trees and up and down. They do a whole lot of walking up and down. So you realize that they could not get the diabetes. So this is randomized control. You pick people, then you bring an intervention and you follow them up to see which of them will develop the disease or not. So at the same time, a group of people is assigned not to receive the exposure. So as you give one set of people a medication, or if they are animals, you give them a drug that will cause a disease in them. Then another group, you don't give them a drug at all, but you give them something we call placebo to establish a placebo effect. Then you find out, you follow all these people up to see which of these two group of people will develop the outcome, and whether that proportion differs from the proportion in the exposed group. So for randomized control trial, if you are looking at animals, you can give them disease, alloxan or streptozotocin. That will give them diabetes or a sickness. Then you give them an experimental drug and see which of them will recover from the drug. So this is randomized control trial, and the evidence is very, very strong. So it is a study design that we use to infer causal relationship. For example, the Medical Research Council vitamin study. The purpose of the trial or the study was to determine whether supplementing or giving a supplementation of folic acid or a mixture of other vitamins with folic acid around the time of pregnancy or conception of pregnancy could prevent neural tube defect. These are central nervous system or spinal cord defects, which are serious birth defects that include spina bifida and anencephaly. Anencephaly means immatured brain. So in the study, this is what they found out, and this study was conducted in 1980. The Medical Research Council vitamin study, that is the name. And this study, which was conducted in 1980, enrolled in a trial women who had previous child with a neural tube defect, and thus they were at high risk of another pregnancy complicated by this problem. So women who had previous children with neural tube defect were enrolled, and these women were divided into 4 groups and assigned to take different combinations of folic acid and other vitamins just before and during pregnancy, because they have children who have the spina bifida. So they want to find out that when you supplement with folic acid, will this problem be solved? Will this congenital anomaly be resolved? So this is what they did. They classified these women into 4 groups. One group took folic acid supplements only. One group also took folic acid plus other vitamins. Another group took no supplements. And the final group took only the other vitamins. And this was their finding. So they realized that out of nearly 600 women who were in the groups assigned to take folic acid, whether with or without other vitamins, they only had 6 children with neural tube defect. So out of all these 600, only 6 children had a defect with women who took folic acid or folic acid plus other vitamins. Similarly, in another group, women who were assigned to take other vitamins alone or no vitamins had 21 affected children. So the number of affected children increased from 6 to 21 when the vitamins were without folic acid. And the focus was on the folic acid supplementation. The other vitamins did not really matter. So the relative risk was 3.5, which was a 4-fold increase in risk of getting neural tube defect. And this difference was statistically significant. Thus, we will say, or they inferred, that there was a strong protective effect of folic acid supplementation on the basis of this study. Meaning that if you take in folic acid, it's going to prevent you from the baby that you produce will not have anencephaly or immature brain, and the baby will not also have neural tube defect, which is a spinal cord anomaly. So the authors concluded that folic acid supplementation starting before pregnancy can now be firmly recommended for all women. So that as a result of this 1980 study, that is why the women who come to the hospital, we end up giving them folic acid supplementation, because we know that it will prevent them from, it will help the brain of the fetus to develop well and prevent them from having spina bifida. So that's the essence of folic acid for pregnant women. So we finished with randomized control trial. So the second guideline is that there should not be any, for us to establish the causation, there should not be any alternative explanation existing. Meaning that we need to conclude that no alternative explanation exists for the association seen particularly in studies that are not randomized trials. Meaning that there shouldn't be different findings or conclusions. Somebody will do a test, a research at Navrongo. Another person will do it at Kintampo, and they end up getting different results, meaning that there is something happening, and that is what we call a confounder. It is important to consider whether the increase in disease rates we see in the presence of a certain factor is due instead to other occurring factors or exposures, and this is called confounding. Confounding means that, for instance, you are investigating a condition, like last time I was explaining, but let's say hypertension. You are looking for a marker, a biomarker, let's say brain natriuretic factor in hypertensives. So if you are looking for a factor such as brain natriuretic peptide, this protein has high level. They are found in high levels in patients with hypertension. So if you have hypertension, the level of this brain natriuretic peptide is very high in your blood. So the level of this brain natriuretic peptide is very high in hypertensives. So what happens? Hello? Hello? Okay, let's continue. So brain natriuretic peptide has high levels. Please mute your mic. Brain natriuretic peptide has high levels in patients with hypertension. So I've explained. Okay, so we have finished randomized control trial. So we are on no alternative explanation. So if there is alternative explanation, it means that there is a confounder. So for instance, like I said, if you have two groups of people. So if you are looking at a study, you are conducting a study, and you have hypertensives. And when you are looking at hypertensives, and you are looking at what? Non-hypertensives. Hypertensives and non-hypertensives. So the hypertensives, you realize that the hypertensives that you have, the hypertensives have what do we call it? They are supposed to have BMP, brain natriuretic peptide, very high. They are supposed to have high BMP. But you realize that the controls are also having high BMP, and there is no statistical significance. BMP over here, you realize that these people have BMP of what? The hypertensives have BMP of 100. Then the non-hypertensives also have BMP of 100 or 101, and there is no statistical significance. So the significant level is what? There is no statistical significance, so it's greater than 0.05, meaning that there is no significance. P value is greater than. It means that, why is it that this marker is supposed to be high in hypertensives than non-hypertensives. But why is it that it's the same? Meaning that we have to look at the people that we recruited. It means that maybe some of the people we recruited were of an age of what? For the hypertensives, we could say that we picked a mixture of ages. So we could say that we selected ages from 20 to 60. And over here too, we selected ages from 20 to 60. So we can say that age will become a confounder. Age will be a confounder. Age is going to be a confounder. It's causing confusion. A confounder is somebody who causes what? Confusion. So age is a confounder over here. Why? Because for hypertensives, normally we know that it occurs in people from 45 years and above. So here, why do we have 20 years? It means that some of these hypertensives who are 20 years, they are not really hypertensive. Maybe the machine or the diagnosis tool we are using are not good. Then the non-hypertensives too, we were supposed to pick what? People from 45 to 60 because it has to be the same as here. But imagine here we pick maybe people who are 10 years to 60, and here we pick people who are what? 40 years to 60. The 40 years, and we are comparing these two groups. So as we are comparing these two groups, they should have the same age range, and they should have the same age range in the hypertensives and non-hypertensives. The age is supposed to be the same. So ideally, if you are considering 45 years to 60 years, then over here to the non-hypertensives should also be what? 45 years to 60 years. And we are not supposed to select less than 45 years to 60 years. So as we have been able to select less than, as we have 20 to 60, and even here we have 40 to 60, then age brings about what? Bias. Age brings about confounding. Because we have to consider age. Age is very important. That's why when you go to hospital, the drug that will be given to a child is different from what will be given to an adult. The same way, the hemoglobin concentration reference range for a child is different from the hemoglobin concentration reference range for an adult. Even women, their reference range is different from men. So we have to consider all these things. So age is very important. If you are selecting people for a study, you should have the same age for the controls and the same age for the test category. Please, do you understand? Please, do you understand? Do you understand? Hello? Hello? Do you understand the explanation? Okay, then let's continue. So we are finished with confounding. So we say that we can take confounding. You can mute your mics now, please. So we can take confounding into account at either the design or analysis stage. Please mute your mics. Okay, so we can take confounding into account at either the design or analysis stages of study. If there is confounding, the association that we see between an exposure and a disease is a distortion. So confounding, like age and any other thing, can influence the results that we are having or the association. Another one is we are still on the no alternative explanation. So in order for confounding to occur, two things need to happen. First, there needs to be an association between the exposure you are interested in and this extraneous or confounding factor. And second, there needs to be an association between the extraneous factor and the disease you are studying. So confounding factor is an extraneous factor. We don't need it in the research. It's just maybe a mistake made by the investigator. Because if you are doing a study and you classify pregnant women, and you say pregnant women who are less than or who are of age between 19 to 25, and you look at the same marker in pregnant women who are of advanced pregnant age or advanced maternal age, and they have age from 35 to 45, and you are measuring the same thing among them, and one is a control and one is a standard, then the age will bias the results, because you should pick the controls and the cases should be of the same age. If they have an age range, it should be the same in controls and cases. There shouldn't be any difference in age, and the difference in age will make the results distorted. You cannot find the actual finding or key finding that you are looking for. So let us look at this. There was a study to establish confounding. So this is what happened. Here we see the results of a study on whether alcohol drinking is a risk factor for lung cancer. That is, are people who drink alcohol more likely to get lung cancer than those who don't? So this study also looked at whether, among those who drink, increasing the amount of alcohol consumed in a day leads to increasing cancer likelihood. So we see the crude and unadjusted results of the study here. It appears that alcohol intake is positively associated with lung cancer. We see that drinkers are more likely to get lung cancer, and those who drink the most heavily are most likely to get it. So let's come to the two by this table. Alcohol intake in grams per day. Lung cancer. So incidence, last time I showed you that incidence is what? New cases of the disease. So we have 7.4, 13.6, 16.4, 25.2. So this is the initial concentration of alcohol. This 0 means that the person has not taken alcohol. Then 0.1 to 12 means that people who take alcohol 0.1 to 12 grams in a day. Then those who take alcohol 12.1 to 24 grams in a day. And those who take greater than 24, these are the heavy drinkers. So we come here. This is the crude relative risk or odds ratio. So those who don't drink, we don't expect their odds ratio or relative risk to be higher. It's supposed to be just 1. And the 1 is the standard or the reference. Above 8 means that the disease appears or the disease is established. Below 8 means that risk factor is a protective factor from getting the disease. So then the adjusted risk factor, later I will show you what an adjusted risk factor is. That is when we remove confounding variables from it. We get the true meaning of the results, and that is adjusted risk factor. For instance, if you are able to adjust for age and make sure that the ages in the controls and the cases are the same, then that result is what we call the adjusted relative risk or adjusted odds ratio. And that is the main results that we are interested in, but not the crude results. So we can see that as alcohol concentration increase, then the incidence of lung cancer also increase. The risk of lung cancer also increase. But when we adjusted, we will move age from it. The risk increase only in those who drank beyond 24 grams of alcohol in a day. But those from 0 to 12.1 to 24, the risk was the same. Meaning that here we have removed the age. We've made them of the same age. Cases and controls were of the same age. So there was adjustment. We've done the right thing. Correction has been made. Confounding has been removed. Ages are now the same. So we don't have any association between alcohol intake and lung cancer, meaning that alcohol does not cause lung cancer when we remove age from our results. So is that confounding by smoking? So people who drink more likely to smoke. So smokers more likely to get lung cancer. So we want to now say that increasing alcohol was able to increase the risk of getting lung cancer. But there should be an extraneous variable. Over here, the extraneous variable is not age, but the extraneous variable is rather smoking. And we say that people who drink alcohol are more likely to smoke. So maybe the smoking is what is causing the lung cancer, but not the drinking of the alcohol. So let's continue. So, but before we decide that this is a causal association, however, we have to ask whether confounding is responsible for this association. You must logically wonder if there is confounding by smoking. So let's go to the smoking and see. So, because smoking meets our first requirement for a confounder, an association exists between exposure, that is alcohol drinking, and the extraneous factor, that is smoking. So research has shown that people who drink alcohol are more likely to smoke than people who don't drink. So we may have a mixing of the effects of alcohol and smoking. So we say that the alcohol and the smoking is the confounder. And when we're able to mix alcohol and smoking, we think we are looking only at the effects of alcohol. So when we look at the effects of alcohol, it was increasing the risk of getting lung cancer. But we say that no, alcohol alone cannot cause lung cancer. There should be another variable, and that is smoking. So when we adjusted, we realized that smoking is the more associated factor causing the lung cancer. So we are still on no alternative. So why might that happen? Because smoking also meets our other requirement for confounding. There is an association between smoking and the disease we are looking at. Here, lung cancer. So smokers are more likely to get lung cancer than non-smokers. So the probability exists that smoking is confounding the association between alcohol use and lung cancer. So you can realize that if you drink alcohol alone, you will not get lung cancer if only you don't smoke. But if you add smoking to alcohol drinking, you are likely or highly susceptible to get lung cancer. So we advise that stop smoking so that you don't get lung cancer. It's not the alcohol that is giving you the lung cancer, but it's the smoking. So the smoking is the confounder. So the effect we think is due to alcohol use may be due instead to smoking, because many drinkers also smoke. So to check this, we conduct analysis that adjust for smoking, and when we do so, we see that there is no association between alcohol use and lung cancer. Drinkers are no more likely to get lung cancer than non-drinkers. So controlling for the confounding, smoking has removed the association between alcohol use and lung cancer, and therefore the association cannot be causal. So over here, we realize that when we adjusted for smoking, when we remove smoking from the analysis, we realize that there is no significant difference between alcohol use and lung cancer. That means when you take in a lot of alcohol, it doesn't cause you to get lung cancer unless you add smoking. So here we have adjusted for smoke, we have removed smoking. When we remove smoking, the effect was normalized. So we can see 1, 1, 1, 1, meaning the standard, meaning that there is no increase in the odds of lung cancer based on somebody drinking alcohol. But unless the person is drinking alcohol at the same time smoking, before he can get lung cancer. Okay, let's go to the third one. The timing of the relationship is correct. An essential feature of an association in order to be considered as a causal is that the timing is correct. Initially, I was telling you that the cause must come first. It's very important. If you're taking a lot of salt, you get hypertension. You don't get hypertension before you take in salt. You get a lot of salt before you get hypertension. If you don't exercise and you eat a lot of fat, you end up getting hypertension or diabetes. So your lack of exercise comes before you get the outcome, which is hypertension. So the timing of the relationship or association should be correct. The risk factor or the exposure should come before the disease happens. Not only must the cause or exposure come before the effect or disease, but there must be enough time for the suspected cause to have an effect. So it shouldn't also be that just one day, if you don't exercise, you get hypertension. But it should be a progressive something that you have been doing over the years. You have been taking a lot of salt over the years, and it will accumulate and give you hypertension. So not only must the cause or exposure come before the effect, but it should be a habitual character that will predispose you to getting a metabolic syndrome. The exposure outcome time sequence can be difficult to establish, and is easier in some type of studies than in others. In prospective cohort studies and randomized trials, exposures are noted at the beginning of the study, at a time when the study participants are determined to be free of the disease. So it's easy to determine time sequence. In contrast, in case control or retrospective cohort studies, records of exposures are obtained or subjects are interviewed about past efforts. So in most of the longitudinal case control or prospective study, prospective is the same as longitudinal. You start a study with the participants not having the disease. Then you follow them up to see when they get the disease. So the exposure status comes before the acquisition or the contraction of the disease. But in the case control study, we look at the disease and those who don't have the disease. Then we look back to trace the risk factors that cause the disease. So we look back retrospectively to trace what caused the disease. So that one does not qualify for what we are arguing about. So in these studies, it's not always clear whether the exposure of interest occurred before or the disease process began. So in the case control study, we don't know whether the disease began before the risk factor, because the disease has already been established and we are just looking back and look at the risk factors that are associated with the disease, but not the risk factors that cause the disease. So case control study and cross-sectional study, we cannot base on their findings and to say that they have causal inference or they are the actual cause of the disease, because they are not strong study designs. It's a randomized control study and the longitudinal studies which are strong study designs. So in these studies, it's not always clear whether the exposure of interest occurred before the disease process began. It may also be difficult to determine time sequence when the time period between suspected cause and the effect. Okay, so for example, you go and read this. They were saying that there was a study done in 1980. Rye syndrome is a disease associated with the liver, fatty liver. So researchers hypothesized that giving a child aspirin for flu or chickenpox increased the risk of the disease in the next few days. But there was one concern raised early on about the proposed association, that children in early stages of children who develop the Reye's syndrome may have been given aspirin as a treatment for the disease, and thus one shouldn't conclude that any association seen were cause and effect, because the effect, that is the Reye's syndrome, may have come before the suspected cause. That's take. So they were saying that when you take, the children took aspirin, they developed the Reye's syndrome. But another school of thought was saying that maybe these children had the Reye's syndrome already before they took in the aspirin, but it's not the aspirin that is causing them to have the syndrome. So this one is just testing for relationship, but it's not inferring causation. But in the timing of relationship, aspirin is supposed to be taken before Reye's syndrome can occur in a child. But we don't know whether the Reye's syndrome came first. The person developed the Reye's syndrome before taking the aspirin. We don't know. So we just test for relationship, and that is the most important. We cannot say that aspirin causes Reye's syndrome. No. It can be that you develop the Reye's syndrome before you took in the aspirin.